So let's take a look at the operations involved in the analysis filter bank. We have a convolution operation and we have a downsampling operation. So the convolution operation is given by this formula here, where x of n is our input signal, h of n is the impulse response of a filter with length capital L, and this sum here goes over only where x of n and h of n are defined. So if you need a revision of convolution, or if you want to go a bit deeper into convolution, you can go to Guitars AI GitHub, and there we will find a repository called Algorithms Repository, where I give some explanation and implementation of very important algorithms in 4 different programming languages: Python, JavaScript, Java, and C++. So there you'll find convolution in 1 dimension, with a short explanation and the implementation in 4 different programming languages. Then there's an example, so it's an application of the convolution in 1 dimension with a moving average filter. There is a convolution in 2 dimensions, and also an example with an application of the convolution in 2 dimensions, which is an image edge detection filter. So you'll find this at the Guitars AI GitHub with the algorithms repository. So going back now, at this point, we have x of n convolved with our filter, and we have this formula. And now we need to take a look at the downsampling. So what is the downsampling operation doing? The downsampling operation is replacing our index n at the higher sampling rate, at this point, and we are replacing by m times our downsampling rate plus n0, which is the phase index. So we're replacing in this, after convolution, we're replacing the index m by m times n plus n0. And we have our downsampled signal that looks like this. So the analysis filter bank is decomposing the signal into different subbands with different frequency bands. So each frequency band has a lower bandwidth and has a lower sampling rate. Later on, we can use bandpass Nyquist theorem, and we can reconstruct the original signal from these subbands.